Yeah, thank you first of all for having me here in this friendly atmosphere and workshop. And of course, I'm honored to be part of your birthday, Harald. I remember the first time I heard of you was when I was a PhD student for my supervisor, Klaus Dietz. And over the years, we have met on and off in various places, I think. I can think of Ringberg, and I think of Japan, and I don't know where else, and also my research has sort of contacted with yours occasionally over the years, although we have not collaborated. But I saw that recently your latest papers have some relation with Calogero models. So I thought it might be fitting if I just report on my own musings about Calogero models, which go back to, let's see, how is this? Pointer is there, yeah. Go back to more than 10 years, but more recently we have found some new aspects of these models. Surprisingly, such an old model, which is a workhorse of integrable multi-particle systems, more than 50 years old. But there's still things to discover. And quite a number of things that I talk here is not original, but some of them are. So if you want to know some references, I didn't put them in here, but you can ask me. I can certainly point to them. So this is essentially two parts. In two parts, one is in this old work together with Francisco Correa and Mikhail Plushai from 2013, and then more recently again with Correa, Insunsu, and Jan Marquette about this Casimir operator. And then that's the first part, and the second part is something that I'm currently pursuing with Correa and Insunsa on new intertwiners that we find in these Calogero models, which seem to have not been seen by others so far. Okay, so let me just give you the basic players. So you see now, I'm more a friend of concrete models and explicit calculations, so this talk is not as formal maybe as some of the others here, but therefore it might appear more technical because they're actual calculations. So this is the standard, the simplest Calogero model. Kinetic term, potential, inverse square potential. Here's a coupling G, which is parameterized like this, so it can be assumed to be bigger than 1/2. Center of mass, momentum, and position. And we look at the quantum model. These are the permutation, the transposition operators that permute two particle labels like this. And then one of the important inventions in the 80s were discovery that a lot of the structure of these Calogero models can be generated by essentially deforming the normal momenta in this way, by adding a term proportional to the coupling. This is first, I think, due to Charles Danko, named after him. And that was used by Dutch group, Heckman and others to discover or to reinterpret a lot of the structure in the Calogero model. So the curious thing about these deformed momenta is that they commute. This is not trivial, and this is a key of their usefulness. This is for the rational model. So I should say this is, of course, the simplest case. There's lots of generalizations of this model. They're trigonometric models. They're models related to other Coxeter reflection groups. Here, this is related to the A-type Coxeter reflection group. Yeah. So this has a simple particle interpretation, unlike the other models. So for example, one of the first applications of this operators is that you can construct all the Liouville charges, n of them for n particles, by simply taking powers, the kth power of this object, summed over the label, the particle label, and then take what is called the residue, which is simply the following. So if you take the kth power, you have an operator that still contains permutations here. Yeah? Now push all the permutations to the right and act with this operator on the totally symmetric functions. So this means after you pushed all the S operators to the right, you replace the result by unity. Totally symmetric function is unity. That gives you some complicated terms, which you will see in a moment. And this, it's easy to see that this construction immediately gives a set of commuting operators. So for every value of k, you get one which I call B0k. You see the 0 in a moment. and or ik for the Liouville charge. So they commute. And so in this definition, the first one is just the total momentum. Then you have the Hamiltonian, the quadratic one. And for example, here's the next one, which is cubic in the momenta. You have such a term here. Now, I could think of writing down more general symmetric observables. For example, these operators here all go back. They all start with the kth power of the momentum. So they are. But what happens if I also take combinations of momenta and coordinates? For example, linear in x and p, quadratic in x, or you see in a moment more general, kth power in x and lth power in momenta. Yeah, so this is just a special case of a more general kind of observables. So this one here and this one here, in fact, are the only ones together with the Hamiltonian that are observables of quadratic in momenta and coordinates, and they form an SL2R or algebra, right? So this is a conformal algebra in one dimension, or well, SL2R. So they're close among themselves. Now I go one step further. I let k and l range over any integer. So look at observables that are formed from the kth power of the coordinates and the lth power of the momenta. Of course, I take this deformed momenta. And since there's no an ordering problem, of course, because x and p do not commute, x and pi do not commute, I just choose to symmetric ordering. So I while order with respect to x and pi. And then, of course, apply to symmetric functions. So this gives me a set of symmetric observables, all of them. And you can, for example, generate, of course, the Weil order products in this way. And this way you get an infinite pyramid of observables. Okay, so every horizontal line is one level. Level means the sum of these two indices. So 0, 2, 1, 1, 2, 0, etc. And it happens so that the left-hand side of this pyramid does not depend on G. For example, you see here 2, 0 is just x squared. And on the right-hand side, you get contributions from the interactions. Hamiltonian, B03, which is written here, and so on. So once you add to the level 1 and level 2 any one of the other higher operators, you can generate them all by taking commutators, higher order operators. And it doesn't stop. You have no, we'll see there are some other infinite dimensional subalgebras, but the whole observable algebra of observable contains all these operators. I need one of them. So, for example, to get this one, for example, I could take this one, 3, 0. Take the commutator of 3, 0 with 0, 2, Hamiltonian. You'll see in a moment, I'll give you the commutator relations in a moment. Yeah, you see that then this when you give you this. SIJ. Oh, that's just a permutation operator. So when you push it through any object with the label I, it changes the label from I to J. It's just a formal operator that permutes the indices. Transposes the indices in this case. Yeah? Just replaces x by j, I by j, and j by I backwards in both directions. So when you appear to use it twice, it's easier than anything. Bosonic Fock space, just ordinary quantum mechanics so these particles, okay, there are two ways of interpreting this. Either you can think of this as n particles on a line, just the ordinary L2 Hilbert space, or you can think of it as a single particle in n dimensions with a peculiar external potential, because all these particles have the same unit mass. So this is just ordinary quantum mechanics as we know it. Symmetrize? Well, I don't symmetrize here. I look at symmetric observables. I restrict myself to symmetric observables that are totally permutation symmetric. In general, of course, you can have an arbitrary Coxeter reflection group, and then you can look at the observables that are invariant under this Coxeter reflection group. all the observables. Let's see, yeah, so we have this. And here is the commutator of X with the deformed momentum. And it looks a bit more complicated. You see there's a commutation operator appearing. All the other commutators are 0. But nevertheless, you can calculate this commutator of 2 arbitrary observables. So if you do that, you see the leading term has a very simple structure. It has this k times n minus l times m prefactor, and then the labels add and -1. Yeah, exactly. This is a W1 plus infinity algebra, exactly. And well, there are subleading terms which come from the, well, which go with h bar powers, yeah, and with definite coefficients. So then the indices get, descend. And they can be calculated in terms of Bochhammer symbols and so on. So there's a definite formula. Although I was a little bit lying to you when I wrote it this way, because this is what you get when you put g to 0. When you put g to 0, of course, you still have an h bar term from here, right? You put it on the other side. X with p is just I times h bar. Yeah. These terms are of higher order of h bar, and they come with a coupling g. But the coupling g, it turns out, enters only in this commutation relation when you have a term b00 that is a constant. So when the indices are such that they are equal, then you get an additional piece. You get not just this term, which is in this formula, but there's another term which depends on g. There's a polynomial of order r in this combination, which has to be added. It's kind of a deformation of the free theory. So the only way the coupling, the Calogero coupling, changes this algebra is by adding to a central part. I mean, the term that comes with the constant b00 is just, as I put here, it's just n times particle number times the identity. That's such a term. The algebra is almost like the free particle algebra. Here are some special cases. For example, the level 2 operators have a very simple action. There's no central terms here. This operator B11 measures the difference between the two indices. And you can see, for example, here, when you take one of the indices to be unity, this is a subalgebra, that stays unity, the second index. So this is just a width algebra. So these are all the operators that lie on this line here or on this line. So these commute, and these commute. These are the Liouville charges, right? And one, sort of the next diagonal, these one form a width algebra, and this one also form a width algebra. This is just part of the infinite W1 plus infinity algebra. This is inside. Okay, so this is for an unrestricted number of particles. However, when you fix the number of particles, and your phase space is finite dimensional, you have only n momenta and n coordinates, then the number of functionally independent symmetric polynomials is finite. So you have too many, infinitely many symmetric observables are functionally not independent anymore. So what happens is that all the Liouville charges with index bigger than n, are functionally dependent on the lower ones. So they can be expressed as polynomials of the lower ones. So you see some examples in a moment. Well, one thing I want to mention is that there's not only the Liouville charges. This model is maximally superintegrable, which means that there are, on top of the n Liouville charges, there are also n-1 other charges which commute with the Hamiltonian, but which are not in involution. They can be constructed also very easily. One way is this way. This combination with an explicit time dependence gives you an object that automatically commutes, is time dependent, sorry. So this is an explicitly time dependent charge. This can be constructed, n-1 of them. Or you could take quadratic expressions in the charges and anti-symmetrize them in the two indices k and l, and then you also get something. You mean here? Well, this is the explicit, the complete time dependence. It's like, think of the in normal Minkowski, in a relativistic theory, you have also conserved charges related to the boosts, right? They're explicitly time dependent. When you compute the full time dependence, you have a term that comes from the time dependence of the. Of course, yeah, they depend on x and t. They're functions of x and p. And x and p, of course, are time when you solve the Hamilton equations, right? They obey the Hamilton equations. So you have the explicit time, there is the time dependence that comes from the commutator, but this is the Hamiltonian here, right? So it's the usual thing in phase space, the total time dependence given by the commutator with the Hamiltonian plus an explicit time dependency. Explicit time dependency is here. Okay, so what is nice about this quadratic version of the extra charges is that they can actually be obtained also, well, a certain set of them, n-1 independent new ones, they can be obtained by taking the Casimir operator of the SL2 algebra. So the SL2 I mentioned has a Casimir, which is this quadratic expression here in terms of Hamiltonian dilatation operator and this K operator. And it generates by the commutator action from the Liouville charges, generates n-1 further. You see that, of course, they commute F2 is identically 0, and you can see because this Casimir operator commutes with the Hamiltonian, I2 is the Hamiltonian, all automatically commutes, they all commute with the Hamiltonian. So this way, this is a neat way of getting the n-1 extra charges that give you the maximal superintegrability of the system. But I will not use this in the future. It's just that mentioned that they form an interesting polynomial algebra. So I want to focus on the first non-trivial example when I restrict the number of particles to 3, just 3 particles. For 2 particles, as a warm-up, things are very simple. We have just these 5 observables, because, as I said, when the index, the sum of the 2 indices is bigger than n, then they are dependent, functionally dependent. So there's only 5 independent symmetric observables. And it is useful actually to subtract the center of mass. You can decouple the center of mass degree of freedom. See, the center of mass is here, the position, and the center of mass momentum, the first 2. And you can get rid of them by forming these combinations. So the primed observables are those that they also form an SL2R, and they commute with the center of mass observables. So this means that the algebra that now this W1 plus infinity algebra now is a finite algebra, right? Because we have only finitely many generators and the algebra is finite. I call it W3 for 3 particles. For W2, in this way, it can be decomposed in the center of mass piece, which is just an Heisenberg algebra. These 2 things, center of mass, momentum, and position form a Heisenberg algebra, and the rest. The rest is an SL2. So there's nothing, this is completely standard. And here's again, the Casimir operator. And yeah. Now what happens now if I go to 3 particles? I have 4 more operators. I go to 1 level higher. Now I have 9 operators. And here at the explicit form, B30 to 1, they do not depend on G, B12 and B303 you've seen before, they depend on the coupling. So these additional level 3 operators now enter the algebra. And well, you can try to calculate the algebra, which the commutation relations with the level 2 generators, the SL2 generators, is standard. All these things form SL2 representations. So the interesting part of the algebra is the commutators of these guys among themselves. And so I have to simplify the notation a little bit. So what I'm doing is I will call, instead of BKL, I just write KL. And since I will look at the universal enveloping algebra, I need products of these B's. And I use symmetric products again. So this is not the same Weil product, Weil symmetrization, because here's a capital W, because this is just a symmetrization with respect to these B's, with respect to these factors, not with respect to X and P. Careful. So I just use this symbol saying this is completely symmetrized in BKL, BMN, etc. So then the commutation relations, here's a table of commutators between the level 3 operators. And you see the commutators give you level 4, right? So here the rule was when you take a commutator, you add the two indices and you subtract 1. So 3 plus 2 is 5, minus 1 is 4. 0 plus 1 is 1, minus 1 is 0. Yeah, so you get a level, you get this operator. But this is already functionally dependent. So you have to express it in terms of the other ones from our set. And likewise here. And you see there are some terms, some lower order terms, higher order in H bar quantum corrections, which come from the further terms in the commutation relation. Now here's a relation how we express the dependent observables in terms of the independent ones. You see there are up to order 4 products. So this needs some calculation. And then also, in this case, we can decouple the center of mass by using, well, new combinations where we subtract the center of mass piece in such a way that these BKL prime commute with the center of mass position and momentum. Now, the task is to rewrite this table in terms of the primed objects and also to express these dependent operators in terms of the independent primed objects. So this is not so simple because it takes, you obtain nested while ordering because you have to insert while ordered objects into while ordered objects and you have to reorder them in order to express them into totally while ordered objects. So there is some combinatorics here. If anybody knows a general formula or recursion formula for such, please tell me, because we did these painstaking hand calculations, and then I'm sure there is some kind of a rule how to do this in general. There's no? No, we did use computer, of course, but it is not very, not very satisfactory to not have a general formula. So this is the result anyway. So here you have the center of mass cleaned operators and their commutation. So here is, now you see the algebra becomes quadratic. And there's a central term here which depends on the coupling. Okay, so, however, this is not a very nice way of writing it. It is more transparent to use an SL2 covariant notation. Mind you that the SL2 generators, this is 2, 0, 1, 1, and 0, 2, are just the generators, sort of the J plus, J minus, and J zero of the SL2. Yeah. The Hamiltonian, the dilatation operator, and this operator K, they just form an adjoint representation of SL2. So let's label them with J, with the index. And the level 3 operators, these 4, they form a spin 3/2 representation of the SL2. You can see, you can derive from the general commutation relations. So I just call them K 3/2, etc., until K minus 3/2. So they form a spin 3/2 representation. And clearly, well, I've normalized them in such a way that the commutators of the J, you have the structure constant of SL2R, and J with K gives the usual, well, this is just the representation matrices of the spin 3/2. So the interesting thing is the coupling of the two spin 3/2 representations. So the commutator of the Ks, what are this? This is something new. And it is something quadratic in J plus a central term. And from representation theory, it's clear when you take the antisymmetric tensor product of two spin 3/2 representation, you get a 2 and a 0, which is the same as a symmetric product of two spin 1 representations. So here you have a spin 2 and a singlet, a spin 0 appearing. And the singlet is just the Casimir of the SL2, which we have been filtering through this algebra. We have been using the SL2 substructure. So this is the Casimir operator. And now with this notation, we can write the commutation table in a nicer form. So here you see how the commutator of different spin 3/2 generators will give you something. The spin 1 generators and some central term. Here, this is the Casimir, and then there's some central piece which is just fixed by the coupling. So this is the complete algebra. So you could write it maybe in one line by saying that the right-hand side here is there's a coupling, basically the spin 3/2 product coupled to the spin 2 representations, the coupling matrices, and then there is a coupling to the Casimir, and there's a central of the algebra looks like. Yes, exactly. Yeah, yeah. When you take h bar, so h bar naively to 0, it is just like the free theory. At least on the level of 3 particles, you don't see the interaction classically. But of course, I should be careful because the classical limit of the Calogero model is not just sending h bar to 0. It is sending h bar to 0, but h bar times g becomes constant. So it's at the same time you have send g to infinity. So the product of h bar and g is the final, because that appears in the, you look at the Hamiltonian, you see you have to, in order to survive this, you have to put h bar times g to constant, right? And then something survives, of course. Okay, so now a little curious thing. We were interested, well, we had for 2 particles, we had the Casimir operator, right? Which commutes with all the generators of the SL2. For 3 particles, we have this bigger algebra, which consists of 9 operators, or 7 operators plus the center of mass. And the question is there also a Casimir operator? Does this nonlinear W algebra have a Casimir operator? And in principle, there should be, because we have 9 generators, but the phase space is only 6-dimensional. So there should be 3 relations. 3 relations, meaning 3 combinations in the polynomial, in the universal enveloping algebra of this W3 algebra. There should be 3 relations, meaning there is some operator that is in any realization proportional to the identity. And well, we tried, and the simplest answer that works is something of order 6. So here's the notation is the following. This is an operator. So this T, these indices mean, the 2 lower indices mean the sum of the first label, and the second index means the sum of the second label. So 0, 0, 0, 2, 2, 2. Yeah? And the power, the upper index, means the number of factors in the product. Prime means we have reduced the center of mass. We've gotten rid of the center of mass. So it is clear because you want to have these guys to commute with all the generators. Commutation with the SL2 generators is easily done. For example, commutation with the operator that measures the difference between the 2 indices is guaranteed when the 2 indices are equal. So this is already taken care of. Then these relative coefficients here are engineered in such a way that these guys commute with the Hamiltonian, so with this guy and also with this guy. So as this ansatz is written now, this already commutes with the SL2 generators. But we have to guarantee the commutation also with the K operators, with the level 3 operators. And since they're all related by SL2, they form a spin 3 half representations, it's enough to test one of these relations. So we have to impose that this ansatz commutes with one of the level 3 operators. This gives a large number of non-trivial relations on these coefficients alpha, beta, gamma. And here, in the first attempt, we put h bar to 0. So let's just look at the classical part. Then the calculation is not so difficult. It turns out this is the solution. So there is a classical Casimir operator if you naively put h bar to 0. So this is like the free theory. Now we are putting h bar to 0, not scaling g. But if we turn on h bar, the commutation relations gives us terms, okay, of new structure, which cannot be cancelled, and you have to also deform the classical ansatz by adding quantum corrections to the classical ansatz for the Casimir operator. And they are of this type. So here the index is lower. Here are the different terms you have to add. And now when you compute the commutator, it turns out, yes, now all the terms are there. There's an overdetermined system of linear equations, and there is a solution. And these coefficients here, now delta, epsilon, zeta, are just given by this expression, and here lambda is just g times g minus 1. Now you see the coupling appearing. So there is the smallest Casimir operator for this quantum W3 algebra is already rather lengthy object. Here it is in full glory. So it is a polynomial of order 6 in the operators without the center of mass. And we can, of course, calculate its value when we replace the momenta by derivatives, just the differential realization of the momenta. And then it reduces to a polynomial, as it should. It must be proportional to the identity, after all, right? It's a Casimir operator. This is the proportionality. Now, if you want to make it even more general, you can try to put the center of mass back in. And then it becomes more complicated. You need to do massive file ordering, and then the expression is more complicated. You get terms up to order 9. Well, the different pieces which I've written here, you can explicitly write over a few pages. This is what you get then. So it's an order, actually an order, I think the order 9, if you look at this first term, 1, 2, 3, 4, 5, 6. Well, there are order 9 terms, like up to order 9 at least, polynomial in the generators. So it's not known, we don't know what the other two Casimir operators look like. We have some ideas how we could try to find them. So it's still ongoing question. So this is basically a challenge to try to see whether we could do this for W3. Okay, now in the last part, I want to change a little bit the subject and talk about intertwiners, which is also a structure that is known for a long time in this subject. And it is related to what the Russian community called algebraic integrability. It goes back to Heckmann originally. He used the Dunkel operators to construct operators that relate the Hamiltonian or any Liouville charge, ik, k from 0 to 1 to n, for coupling G and coupling G plus 1. So it shifts the coupling. So some people call it shape invariance. The two different Hamiltonians, Calogero with coupling G and coupling G plus 1, are related. And their spectra, this means their spectra are they are isospectral. Because you can map eigenstates of one of the Hamiltonian with this intertwiner to the eigenstates of the other one. And so this is the basic relation. You push this intertwiner M through the Liouville charge, and you get the Liouville charge with a shifted coupling. And the Dunkel operators again play a key role, namely, in this case, you don't take a symmetric polynomial of the Dunkel operators, but you take an antisymmetric polynomial. This is the simplest totally antisymmetric polynomial. It's the product of pi I minus pi j. And take on symmetric functions. And this, in fact, is easy to prove. This gives you an operator that does this job. Now, the immediate consequence of that is, well, you have also the inverse. You can go back with the formally adjoint. Take G, you flip the sign of G, then you can go back. Then nothing prevents you from going from G to G plus 1 and then going back. Then you have an operator that commutes with everything. So is that a new charge? No, because you can prove it is again a polynomial in the Liouville charges. So it's not a way to generate new charges. In fact, well, maybe I'll spare you the details. You can calculate, because the nice thing about this algebra is, when you take the commutator of these operators, because the operators have this potential in them, 1 over xi minus xj. But the algebra, the coefficients in the algebra never depend on x. So you can compute the algebra by sending the positions all to infinity. The potential disappears. This means that the coupling constant in this algebra, at least for those terms that disappear in the limit xi going to infinity, cannot depend on the coupling. So you might as well make some computations easier by computing them at zero coupling, the free theory. So this can be done here, for example, this case, and you get that this polynomial in the Liouville charges is, here's some examples, is some definite polynomial. 2 particles, for example, you get this. For 3 particles, you get this. So Here are the Liouville charges 4, 3, and so on. 4 is, of course, dependent, and you express in terms of the independent ones. Again, you get this higher order polynomial, and so on. These can be easily calculated. Okay, so this is for generic couplings. But when coupling is integer, it means that you can relate the theory to a free theory, right? Because you start from g equals 0. Any integer value of g by a finite number of intertwiners, you can reach this from the free theory. And so let me define basically a bold M, which is just the product of intertwiners coming from the free theory all the way to coupling G. So these intertwiners directly go from the free theory, or the coupling 1 is also the free theory, because remember we had G times G minus 1. So G equals 0 and G equals 1 is both free. Equals 2 is the first non-trivial interaction. And then, okay, in fact, this leads to another Liouville charge in the following way. Namely, you can now, let me through this. Let me go through here. So I take the intertwiner at 0 coupling, which is just, here you don't have the default momenta, pi I minus pi j, but for 0 coupling, it's just the ordinary momenta, yeah, this object. And dress it, so-called Dabu, dress it with this intertwiner from left and right. And then what you get is this chain, where here I have the inverse intertwiner, and here you have the intertwiner. And this relates the theory from coupling 1 minus g to g. So this object Q goes from 1 minus g to g, but the coupling at 1 minus g, if you look at the way the interaction was, everything is always a function. Well, not everything, but in the Hamiltonian and all the Liouville charges, you have this combination. So this is invariant under this flip. So this means when I have a chain of intertwiners relating me from 1 minus g back to g, it means I have closed the circle. So I have found a new object that commutes. And in fact, it's a new charge. A new conserved charge is algebraically independent on the previous charges. So it actually gives you a 2nth charge, one more than you would expect from maximal integrability, superintegrability. That's what the Russians call superintegrable, and not analytically integrable, sorry. So you can maybe see it easier in these diagrams. Here is the Hamiltonian, the free Hamiltonian, then you intertwine, you go up in the coupling. Here is the sort of the accumulated intertwiner from the free theory to the interacting theory, and here is the intertwiner that starts from the Hamiltonian coupling G, or 1 minus G, which is the same, and goes all the way up to G again. So this is an object which intertwines from the theory to itself, and therefore is a commuting charge. So you have an extra, but only for integrable values of G. So one can check, one can take its square, and its square is actually, again, a polynomial in the Liouville charges. So the reason why it is not in the original set of conserved charges is because formally it is a half integral power of the Liouville charge, of the polynomial. Its square is a polynomial in the Liouville charges, but it's an odd polynomial. So you cannot take the square root. Yeah? It's, in that sense, formally it's a square root, but it means really it is an independent, functional independent charge. And you can compute now the full algebra of the Liouville charges, the other conserved charges, this new charge, etc. Well, no, we did this in 2013. And just to show you some examples, for the three-particle case, here is the intertwiner. So this is pi 1 minus pi 2 minus pi 3 minus pi 1. And you work it out. Well, it simplifies a bit when you pull out these factors, but when you put them back in, this is the operator. So you have here an operator which is cubic in momenta and explicitly known. So for this, you can push the Hamiltonian from coupling G to G plus 1. A three-particle Calogero. And then you can compute, for the simplest way, for the coupling, first non-trivial case, you can compute this new charge, and it's of order 9. Okay. So finally, I want to say a few words about some new intertwiners that we discovered just last year. And it goes back, as often, to very old work by these gentlemen, because they wrote a paper where they generalized the integrable Calogero model. So here is the Hamiltonian. Now I put an index n for the particle number. I make it explicit. Okay, so this is the n particle Calogero model with coupling G, and I add a free particle, an n plus first free particle. I call this Hn plus 1. And now I turn on an interaction for this extra particle. I make it interact with the other particles in the usual way, but with a weight here which depends on the coupling G. So this is a little bit non-standard. This is not just the difference squared, but it depends on the, unfortunately, depends on this coupling here. Well, what this group of people showed is that this model, this deformed model, is algebraically integrable also because there exists an intertwiner, W tilde, which relates these two models. So we can push this operator through this Hamiltonian and turn on, in this way, this funny coupling of the extra particle. Now, this is, of course, not a Calogero model because the coupling, this coefficient should be unity for a normal Calogero model. But it is unity for G equals 2. It's the only case where it is unity. So for G equals 2, in fact, it is the Calogero model with one particle more, n plus 1. I should say, actually, this model trivializes in the classical limit. It is only a quantum model because this term, you see, when you take the classical limit h bar g to constant, but h bar to 0, because there's no g squared here, this term will disappear in the classical limit. So it is only a quantum integrable system. Okay, and so this got us to the idea to search maybe for an intertwiner that generalizes this relation for higher coupling. Not like this one, where you have this funny coefficient, but for the normal Calogero model. So something where you push it through the nth particle Calogero model plus one free particle, and you get the full n plus 1 particle model. G to infinity, but G minus 1, yeah, that's a, no, but H bar, yeah, but that one you see also it goes to 0. If you send H bar, if you keep H bar G fixed and send H bar to 0, then this disappears. And I think even if you send, let's see, oh, well, you have a square, or you have a square, okay. Yeah, we see it's even worse, right? Because then you have another factor of G here. It disappears for sure. Yeah. Okay. So we were not very optimistic first because this we thought this for sure has been discovered. This should be known, yeah, and this will not work. But it did work. So together with the horizontal intertwiners, now we have some kind of a network. So here is the sort of n particle model. So of coupling 1, coupling 2, etc., coupling 3, integer value of coupling, and let's add one free particle. This particle is just a spectator. It doesn't see. It is not seen by the intertwiners here, right? It's just added, it writes for free. And we can use these intertwiners to step up the coupling in integer amounts. Now the new thing is that we have postulated and we find that there's this vertical intertwining which actually turns on the coupling of this extra free particle with the other particles. Turns it into a full n plus 1 particle model with the same coupling. So the coupling is not shifted. And since for coupling 1, we have the free model on the left, on the very left side, all these models are the same. Right? So this model is the same as this. And now, so we have this chain. And of course, in order to get the network, we need again to add one more free particle. So this is not exactly the same, but it's kind of a trivial relation. From here, from this line to this line, you simply add a free particle. Then you can go from n plus 1 to n plus 2, n plus 2 to n plus 3, etc. And this means, if you look at this rectangle, you have some recurrence, some kind of recursion relations between these different horizontal and vertical intertwiners. And you can, in fact, know how their leading terms should look like. So here is the term that doesn't depend, well, the leading term has to be of this form, and then there are higher terms which depend on x and depend more on coupling. So it's an operator of an order which increases with n and with the coupling. And we have no proof of its general existence, but this or its construction is a factorization problem. So either solve this recursion, so if you have Wn, you look at the left-hand side, you try to factorize this left-hand side in this way. Or alternatively, instead of looking at this object, you can write this object as, well, if you go from here to here, it's the same as going directly from here to here. So this will give you another kind of factorization problem. So for the accumulated intertwiner, so you have this we know, and the question is, can we factorize this guy in this way on the right? And, not an obvious problem. Of course, you can, what I should say, you can find operators that do this job by going from here backwards, going up and going to the right again. But these operators will be of higher order. They will be of higher power in the momenta. So they exist. But the question is, can we find an operator of this order here? And indeed, examples are, for example, for two particles, coupling 2 looks like this, fairly simple, coupling 3, and we have convinced ourselves it works up to coupling 5, and then we have a general proof of existence using some mathematical factorization paper up to coupling 7, but we don't have a general proof. So this is a new, maybe interesting structure in this business that now allows one to relate the Calogero model for any integer coupling, any number of particles, basically to the system of free particles with smaller number of particles. I think my time is coming to an end. So I should just wrap up by saying that, as it was already mentioned, there's a W1 plus infinity algebra in the Calogero model. And if we fix the particle number, then this is a finite nonlinear WN algebra. And we can easily characterize the conserved charges using the Dunkel operators. We have constructed the smallest Casimir operator for the first non-trivial case, already rather involved. Well, I didn't say that, but it's much more easy to construct a classical limit. So just putting h bar to 0, the first part of the calculation, yeah, where the coefficients were just like 4, 6, and 9. This operator can be, of course, found by using demanding vanishing Poisson brackets of this operator. And this gives you partial differential equations. These can be solved much more directly. So this is maybe a good, maybe a chance to go to higher Casimirs classically first. Yeah, horizontal intertwiners are known for decades, and they show that the spectrum doesn't change really when you step up by integer coupling. But now, yeah, and then there's an odd charge for integral coupling on top of that. But what is new, it seems, is intertwiners relating n and n+1 particles, which we showed for the Hamiltonian. But we haven't tested whether this vertical intertwiners also work for the other Liouville charges. Presumably they do, but we don't know yet. If we have n Liouville charges, we could check possibly whether they work also for the other ones. And the picture a little bit more. Yeah, so that's what I wanted to say. Thank you for your attention, and happy birthday, Harald. So I dug out this picture from my files. Maybe you know where this is, but probably it's not so easy.